Good day, everyone. We are from the Department of Statistics of the CUHK. Thank you for joining me today. I am going to talk about the fundamental concepts of probability, focusing on the law of large numbers. This is a very important topic in statistics, as it tells us how we can use samples to approximate population parameters. In this presentation, I will introduce the weak law of large numbers, prove it using Markov and Chebyshev inequalities, interpret its meaning and implications, and illustrate it with some examples and exercises. I will also make some remarks at the end. Let's start with the introduction. You can see a question on the top. If a coin has been flipped 9 times, landing on head each time, what will be your prediction for the 10th flip? How would you answer this question? Do you think that tail is more likely to occur for the 10th flip, because head has already appeared 9 times in a row? Or do you think that head and tail are equally likely, because each flip is independent and random? This question relates to the concept of probability, which is a measure of uncertainty or randomness. On the next page, you can see some definitions of terms that we will use throughout this presentation. A population is a set of all elements or data that we are interested in studying. A sample is a subset of elements or data that we draw from the population. A population mean is the average value of the population. A sample mean is the average value of the sample. For example, if we want to study the height of all students in this university, that would be our population. If we randomly select 100 students and measure their height, that would be our sample. The average height of all students in this university would be our population mean. The average height of our 100 selected students would be our sample mean. So what is the difference between them? On the next page you can see an equation that expresses the relationship between population mean and sample mean. The equation says that as the sample size n approaches infinity, the sample mean x bar n converges to the population mean mu. This means that if we take a very large sample from a population, the average value of our sample will be very close to the average value of our population. This is actually the law of large numbers, which is one of the most fundamental results in probability theory. On the next page, you can see an example that illustrates this result. Suppose we are rolling a fair die, which means that each number from 1 to 6 has an equal chance of appearing. Let x be the number that we get in one trial. The expected value or population mean of x is 3.5, which is calculated by adding up all possible values of x and dividing by 6. Now suppose we roll the die 3 times and get 5, 6, and 1 as our outcomes. The sample mean of these 3 numbers is 4, which is calculated by adding them up and dividing by 3. You can see that 4 is not equal to 3.5, but it is close to it. If we roll the die more times, say 1,000 times, we would expect our sample mean to get closer and closer to 3.5. This is what the law of large numbers tells us. On the next page, you can see a graph that shows how the sample mean changes as we increase the number of trials from 1 to 1,000. The horizontal axis represents the number of trials, and the vertical axis represents the sample mean. The red line shows the population mean at 3.5. You can see that as we roll the die more times, our sample mean fluctuates around the population mean, but it does not deviate too far from it. In fact, most of our sample means are within 1 unit from the population mean. This concludes our introduction section. In summary, we have learned what probability is, what population and sample are, what population mean and sample mean are, and what law of large numbers is. We have also seen an example in a graph that demonstrate this law. Now we come to the proof part. In this section, I will show you how to prove the law of large numbers using some mathematical tools called Markov inequality and Chebyshev inequality. These inequalities are useful for bounding the probability of rare events. Please look at the next page of the presentation. You can see the statement of the weak law of large numbers, which is a specific version of the law of large numbers. The statement says that if we have a sample consisting of n independent and identically distributed random variables, denoted by x sub 1, x sub 2, and so on, with a finite population mean mu and a finite population variance sigma squared, then the sample mean x bar n converges in probability to mu. This means that for any positive number epsilon, the probability that the sample mean is more than epsilon units away from the population mean goes to 0 as n goes to infinity. On the next page, you can see the proof of this statement. To prove it, we need to make two assumptions. The first assumption is that the random variables are uncorrelated, which means that their covariance is 0. The second assumption is that the population variance is finite, which means that it is not infinite or undefined. These assumptions allow us to simplify the variance of the sample mean, which is equal to the sum of the variances of the individual random variables divided by n squared. Using these assumptions, we can show that the variance of the sample mean is equal to the population variance divided by n. You can see how we use Markov inequality to bound the probability of rare events. Markov's inequality says that if we have a non-negative random variable x with an expected value mu sub x, then for any positive number a, the probability that x is greater than or equal to a is less than or equal to the expected value of x divided by a. This inequality gives us an upper bound on how likely it is for x to be larger than a given value. To prove this inequality, we use integration by parts and compare two areas under the probability density function of x. On the next page, you can see how we use Chebyshev's inequality to bound the probability of rare events. Chebyshev's inequality is a special case of Markov's inequality, where we let y be a random variable. It is the squared difference between y and its expected value mu sub y. This quantity measures how far y deviates from its mean. Chebyshev's inequality says that for any positive number k, the probability that y is more than k units away from its mean is less than or equal to the variance of y divided by k squared. This inequality gives us an upper bound on how likely it is for y to be far from its mean. To prove this inequality, we use Markov's inequality and substitute x with squared. On the next page, you can see how we use Chebyshev's inequality to prove the weak law of large numbers. We let y sub n be the sample mean minus the population mean, and we let epsilon be any positive number. We want to show that as n goes to infinity, the probability that y sub n is greater than epsilon goes to 0. To do this, we apply Chebyshev's inequality and substitute x with y sub n and k with epsilon. We get that this probability is less than or equal to the variance of y sub n divided by epsilon squared. But we know from our previous calculation that the variance of y sub n is equal to sigma squared over n, where sigma squared is the population variance. Therefore, this probability is less than or equal to sigma squared over n epsilon squared. As n goes to infinity, this expression goes to 0. This means that as n goes to infinity, the probability that y sub n is greater than epsilon goes to 0 as well. This proves the weak law of large numbers. This concludes our proof section. In summary, we have learned what Markov inequality and Chebyshev inequality are, how to prove them using integration by parts and substitution, and how to use them to prove the weak law of large numbers using simplification and limit. Now let's move on to the interpretation section. In this section, I will explain what the weak law of large numbers means in plain English and why it is important for statistics. You can see a theorem that states the weak law of large numbers in mathematical symbols. The theorem says that as n goes to infinity, the probability that x bar n minus mu is greater than epsilon goes to 0 for any epsilon greater than 0. This theorem can be interpreted as follows. As we increase our sample size, our sample mean gets closer and closer to our population mean with high probability. Next, you can see some implications of this interpretation. The first implication is that it gives us an accurate approximation of the population mean using our sample mean. Secondly, it tells us that larger samples give a more accurate approximation of the population mean. Let's illustrate this with some examples. Our first example involves drawing cards. Suppose we have cards numbered 2, 5, 8, 12 and 15. Each card has a different probability of being drawn. If we draw a large number of cards with replacement, what would be the sample mean? The answer is approximately 4.96, which is calculated as the expected value of the number drawn. Here is the simulation result that illustrates the law of large numbers. In our second example, we consider a bag containing coins of 3 different colors: green, red, and purple. Each color corresponds to a different amount of money you'll get. Green ones are $10, red ones are $20, and purple ones are $30. If you pick coins from this bag many times with replacement, how much money will you get on average? The answer is $20, which is the expected value of the amount of money you will get. Here is also the simulation result that illustrates the law of large numbers. Finally, let's revisit the gambler's fallacy. If a coin has been flipped 9 times and it has landed on heads each time, what is your prediction for the 10th flip? Some might think that tails is more likely to occur for the 10th flip to balance out the previous results. However, this is not correct. Each coin flip is an independent event and follows a Bernoulli distribution. If we flip the coin for 1,000 times, the sample mean would be 0.5, indicating that heads and tails are equally likely. To conclude this presentation, we will have an exercise on the topic of the Monte Carlo integration and the law of large numbers. We start with a function f defined on the interval. We assume that the absolute value of f integrated from 0 to 1 is finite. We then introduce a sequence of independent and identically distributed random variables, u1, u2, each following a uniform distribution on. We define in as the average of f for k from 1 to n. The question we pose is, does n converge to the integral of f from 0 to 1 as n becomes very large? The answer lies in the weak law of large numbers. As n approaches infinity, the probability that the absolute difference between n and the expected value of f exceeds any positive number epsilon approaches 0. This implies that n converges in probability to the expected value of f, which is indeed the integral of f from 0 to 1. This exercise illustrates 2 important concepts in statistics. The independence and identical distribution of random variables. The significance of a large sample size, which can be determined by techniques such as confidence intervals. Finally, the example we just showed shows how the law of large numbers actually works and its importance in statistics. It shows us that large samples are better than small samples for estimating population parameters. And dispel common misconceptions about randomness and probability. This concludes this lecture on the law of large numbers. Thank you all for watching and participating. I hope you all enjoyed our class today and learned something new and useful. If you have any questions or comments, you are welcome to leave a message below the video, or contact us again. I wish you all a good class today.